A 6,500 Newton per Coulomb uniform electric field is directed to the west, or left, however you want to say it. An electron is released from rest inside the field. There's the negative charge electron. Draw a free body diagram, show the direction of the electric force acting on the electron, find the magnitude of that electric force, determine the acceleration of the electron, and what is the velocity of the electron after 2 nanoseconds, right? Nano, 10 to the minus 9. How far will the electron travel in the first 4 nanoseconds? And what is its velocity after it has traveled 25 centimeters? Look at this. We have a kinematics problem. Draw a free body diagram and show the direction of the electric force acting on the electron. Electrons have a negative charge, so the electric force on the electron is directed opposite to the electric field. So our force is going to be to the right, just like this. We don't need to include mg in our free body diagram because the mass of the electron is 9.11 times 10 to the minus 31 kilograms. And if we calculate its weight, or mg, we multiply that number by g, and we get 8.93 times 10 to the minus 30 newtons. That value is much, much less than the electric force, which we're going to solve for next just to prove it to you. Also because we were asked to. We use our expression relating force to electric field, and we're just interested in the magnitude now. Why? Because we already have the direction. So here's our charge, and here's our electric field, and we get a magnitude of 1.04 times 10 to the minus 15th newtons. So even though that's very tiny, it's still about 10 to the 14th times greater than the weight calculated on the previous slide. Determine the acceleration of the electron. Well, the electron has a mass over here, and we can use Newton's second law to solve for the acceleration. Sum of the forces is ma. Acceleration is the force over m. Here's our force. Here's the mass. And our acceleration is 1.14 times 10 to the 15th meters per second squared. What is the velocity of the electron after 2 nanoseconds? Well, they didn't tell us if it had a velocity in the beginning, so we can say it has an initial velocity of 0. We found the acceleration from part C, and we have time. So what equation do we want to use? First kinematics equation. So v is v0 plus at. That's 0. We just multiply the acceleration times the time, and we get a velocity of 2.28 times 10 to the 6 meters per second. How far will the electron travel in the first 4 nanoseconds? Well, once again, initial velocity of 0. We found acceleration earlier. We'll say it starts at position 0. That's fine, because we just want to find the distance from where it started. So we'll just say 0 for the beginning. We have time. 4 nanoseconds is 4 times 10 to the minus 9th seconds. So here we go. First kinematics equation. Get rid of these two terms. That's nice. So it's 1/2 at squared. Here's the acceleration we found. Here's the time. And a nanosecond is 10 to the minus 9th seconds. Be sure you square this. So many people forget about this square in the first kinematics equation. We get 0.00912 meters, or you can turn it into millimeters by moving the decimal 3 to the right, 9.12 millimeters. What is the velocity of the electron after it has traveled 25 centimeters? They didn't give us a time. Okay, so right away we jump to the third kinematics equation. Our initial velocity is still 0. We're saying we started from x0 equals 0. So the whole equation boils down to just 2ax is equal to v squared. Take the square root of both sides and just plug in our numbers. There's 2. There's the acceleration we found earlier. And here's 25 centimeters. And again, centimeters to meters, move the decimal 2 places to the left. Make sure you take the square root. And you will get the velocity is 2.39 times 10 to the 6 meters per second.